Okay, apologies for that. Obviously, I was too close to the microphone. The core services, the key strategy at AWS with the platform is really to provide broad and deep core services. This core services really are the foundation or the primitive building block on which many other services and specific applications are built. So for example, compute. We have very different flavors of compute designed for different use cases, high memory, high CPU, high network, things like that. In the database side, we provide specialized databases for relational, non-relational caching, and that includes into data warehousing as well. But also, on top of these core services, we provide application services, rich platform services. So analytics, for example, in real-time streaming, and we're going to be talking about that during this morning's session. And these are where we take those primitive building blocks, the core services, and build on top of them higher value, different areas of addressing different areas of customers' requirements. And that's all driven by customers in the way we shape our products. And what you can see there in the application services, these are ideas that customers have flowed back to us, and we represent them back as managed services. And this strategy is working. The recent Gartner Magic Quadrant has AWS Amazon Web Services up in the top right corner, and that's a result of a lot of the way we implement this strategy into the market, but also the richness of the services that we are very proud to deliver. So let's jump into big data itself. In terms of how we see just generically the flow of data, it's very important when we understand data through its different stages in what we call the big data pipeline. So data comes in, raw data comes in, the primary phase then is the collection and storage of that data, processing that data, and then analyzing and understanding that data so we have answers and information. We think of these primitive patterns that really represent primary challenges for our customers. Along these sort of lines, with data collection and storage being a big data challenge, given the velocity and volume of data flowing into a big data use case. And next, as the data moves down, event processing. And this is a newer area, which I'll elaborate on in the presentation. It's really about taking data, streaming data, and acting upon it in real time. And when we actually break down the categories, if you like, the data collection and storage and event processing are very time-centric. They're driven by a real-time need to do things with data, whether it's collect and store, persist that data, or to represent it back to the application in some way via notification, aggregation, something like that. And so, as I mentioned, we'll jump into those. At the back end is really the data-centric part of the pipeline, where data processing occurs, and really data processing and analytics are integral to each other in that preparing data for visualization and understanding is an iterative process where the understanding of that information then requires more data to be enriched and structured and so forth. And so that's very much in the area of BI, big data, business intelligence and warehousing, and we'll cover that as well. So when we apply our products, the AWS services, these are the platform. These are the core products in the AWS Big Data Platform. And as you can see there, they serve different purposes depending on their phase, the data phase of the life cycle that they are serving. And so when we look at data collection and storage, for instance, with S3 Kinesis, DynamoDB, and I put in Aurora as well, RDS, really because there is a tremendous amount of structured data inside relational databases that is a very good, rich feed for big data use cases. Now, what we see and why we have different services addressing different types of data as it comes in is really because the format and the variety, if you like, of data presents different challenges. So, for example, we see data in three primary formats as it enters the big data pipeline. File format, most people are familiar with, just basic files which are great for things like media, documents, and so on. We think of these also, they often are loaded as sets of records. And I think that's an important concept, because if you're batching individual records into files and then loading them up, then streaming is something that may be very appealing, because that's when we go to the next level, streaming, and those individual records are now ingested individually into the data stream. So rather than kind of a batch and load approach of the file, individual records come in via a streaming service. And so there's quite an important difference between file and stream. Transactional is really where we get back to the history of largely databases, but relational databases, but more so NoSQL. NoSQL has really taken off in this, in servicing these sort of use cases because it's originally designed for and serves very well very high scale write volumes. And so the transactionality of that data, in other words, means the immediate read after write and the interaction requirements of that data makes it different to streaming. The data is structured, so you interact with different attributes of the data, but also the reads and maybe subsequent updates to the data are very time sensitive and happen in real time. And that's when we introduce concepts like consistent reads and eventual consistency. So with these, we map the services to these types of data ingest. We presented this in the earlier slide, S3 for files. It's an object store, trillions of objects maintained there. Kinesis is our streaming media platform for ingesting records at a very high rate or a very low rate. The point is to get the data in a nice, easy fashion, scale it to wherever it needs to be, and then make it available for other services to consume. And DynamoDB and Aurora, RDS. Aurora is an engine in RDS. Aurora is specifically designed by Amazon to be a very high-scale, MySQL compatible database. DynamoDB is a NoSQL database, data store that provides simple relations in as long as they're within a single table. So there's no joins across tables. That's a function of NoSQL. But within the table, we have simple relations and even more complex ones in the representation of data in a JSON format. When we talk about streamlined data collection, really the challenge here is really not just to get the data in and persist, but to persist it in a durable manner and make it very highly available and highly accessible to all the consumers. The primary benefit here is, of course, around velocity. It's really to say data can come in at any rate, at any level of granularity, and make itself available for downstream consumption. So, for example, upgrading existing applications. We see this a lot, where we have existing applications that have operated on their own without, the so-called big data tag, or without being integrated into a big data platform. But they can be, and the process we've seen customers adopt is really just to kind of go into those apps and start putting some code to emit records, emit instrumentation. We call this the instrumented application, where that data kind of logs out into into part of the platform, generally either a Kinesis or a Dynamo, NoSQL or a streaming style. And instantly that data now becomes useful, for an analytics process to understand customer behavior within the application, buying, purchasing, so on, depending on what the application is. The other value of increasing the velocity of data is really new applications born in the cloud, which are really designed for streaming from the outset. Built for streaming is a kind of very powerful concept, because what it implies is that you can do things in real time, record by record against that data, and make it a very personalized experience if it's for customers using the service. And a good examples would be where you get real-time suggestions on if you're browsing something, say on a retail site, and you get suggestions on other things that may be of interest. And that's based on analytics at the back end, but servicing those analytics in real time at the front end by recognizing the event stream and then showing a catalog item parallel to that. So if we look at how this sort of platform would play in a social media environment, we've got a few configuration architectures that I want to show, and this one's an interesting one. The example here is if we're taking in tweets from Twitter and making them available in an analytics platform. So there's a few things here. One is we would front end that with Kinesis, because that's a wonderful platform for ingesting unstructured data, where we have a key and a payload, a blob, which is Twitter, right? If you think about the structure of that data. But what you want to do is get into that data and understand it more. And so we then have this second tier of Kinesis-enabled applications. And these are applications that talk directly to the stream and do different things. So this is where we define the consumption patterns. What do we want to do with this data? Do we want to process it more? Do we just want to archive it? Do we want to move it around, integrate it with some other data, and so on? And so in this example, we've got it flowing into S3 and then down into Glacier for basically that's the archive pattern, but also then loading it up into Redshift. And on the top flow, and on the bottom flow in parallel, we could flow that into a custom application that would consume that data in a very specific way according to the application. So the point about this is a very simple kind of architecture. If we apply a few numbers to this, here are the costs of those services. The point being here that, you know, having a lot of tiers is not necessarily a bad thing. It's in fact a very good thing when they are specialized tiers. Each of these tiers each of these components is designed very specific for the purpose in this reference architecture, and therefore it's cheapest at doing the role it's designed to. So you can see the prices there. When we roll this up and we talk about ingesting and managing, persisting and processing, analyzing 500 million tweets a day, about 5,800 tweets a second, all of this rolls up to less than $2.90 an hour. So that's the cost of a lot of that infrastructure, specialized infrastructure. The other point about it being is not only is it inexpensive when it's optimal, when it's efficient, but because it's managed, the human effort to manage those, the administrative overhead is minimal. So when we think about streamlined data collection and how customers are getting benefit out of this, really, you know, think about logging patterns. What can I do with logging in general, you know, as a pattern? Not file logging necessarily, but logging patterns, logging records, logging transactions, as well as logging files. And we see a lot of customers doing instrumenting existing applications. I described that a little bit before. The purpose or the approach they take here is to really inject that logging pattern, the code, into their application to basically start pushing the behavior or the analytics, the metrics that they've collected inside the app into a logging stream. So an example here was done years ago in the Washington Post labs, WAPO labs. They defined this product called Social Reader. It's now evolved substantially a long way from those days and it's now known as Trove. But back in those days, and this is a very early pioneer of social reading, it's a very interesting use case because it's since become very popular across a number of platforms. But essentially what they did was you know, they had an existing application that they barely touched. They injected a few logging puts essentially into the application and then emitted that stream into a DynamoDB table. And so what you're doing now is capturing those data into a table, and of course you can do a lot with that data from there on. And so the representation to the user of this system was that a screen would pop up on the right-hand side of the browser, which would basically show what your Facebook friends are doing or interested in, what are they reading, and it would share that with you. So the idea is, of course, that you share what you're reading, they share what they're reading, and mutual friends with mutual interests find news in different ways. And so that whole entire right-hand side of the screen was powered by a completely different stack, but integrated with these simple injections of put and get calls. When we think of the granularity of data, this is another advantage to putting a platform in place to catch the logging information at high scale. It's really because if you think of like the IoT challenge, where we have a number of customers who run devices, and of course we collect data, and a certain amount of data on those devices. That data is a certain size, and we collect at a certain frequency. As we have a platform that can scale, then better quality data comes from higher granularity, and that means, you know, not only are we selling maybe more devices to more customers and maybe more devices per customer, but we can also enrich our data collection, collect more items, larger items, and collect it more frequently. Now what that does, it sets up a compounding pattern there where the scale becomes an enormous challenge. And this is why adopting a platform that will scale up front is very important. But the quality of that data, the higher granularity, makes the analytics of that data much higher value. Now, if we move through the pipeline, what we did, we took with processing really along that boundary of time versus data. What do we do with data in real time? And this is an area that's become very popular recently. We call this event processing. And essentially the products, the services from AWS under the covers that enable this are AWS Lambda, which is a fairly new product, a very interesting one, which we'll jump into, and KCL. KCL is the Kinesis Client Library, so applications that support that. And we saw them in a previous reference architecture. The enabling capabilities is essentially a stream. In terms of Lambda, Lambda is a function in the cloud. So essentially, underneath the covers, it's all compute allocated with with load balancing and auto scaling and things like that. You could build that yourself. But if you've got a function that just needs to run 20, 30, 50 lines of code in a discrete fashion, that's a lot of heavy lift to get those few lines of code to run. So this is why we designed Lambda. It's really to enable you to say, just focus on the code and we'll do the rest. Handle the scalability, the load balancing, and so on. And so Lambda interacts with event notifications for S3. So when files arrive into S3, that can trigger a notification and then a function based on that. A good example there would be loading files into S3, media files, say pictures, would then automatically trigger a put of the metadata associated with that file into like a fast metadata store like DynamoDB. So you would automatically, you just put the data up, the big file up into S3, and then it would automatically index. Kinesis is a stream, of course, so it's the primitive for a lot of this event processing itself. And DynamoDB is also not quite launched yet. We're in preview mode with DynamoDB streams, but that will be launching shortly, and we announced that at reInvent last year in November. The idea is very similar for both of these, the ingestion point being different depending on the format and the type of data coming in, whether it suits Kinesis or Dynamo. But the emission of that data from those services is very similar, and that's why KCL, Kinesis Client Library applications, support them both, as does Lambda. There's really two main processing patterns where we talk about stream processing in real time, where as events come in, they trigger activity. Very simple data computations, simple aggregates, filters, sliding window, and so on. And then we have the micro batching, which is really, think of more of time-based rather than event-based triggering. So every period, and usually a short period, near real time, we're taking small batches of data and doing things with that. So you get a larger set of data to do aggregations against, for example. So this is a very standard processing and query engine for doing what people are referring to as real-time analytics, where they have a small set of data and then do some quick analysis on that to give an output, a meaningful output. The other thing about event processing is, and requiring streaming as a high-quality source, is really that most people are already doing some sort of streaming at the moment anyway. This has evolved from the behavior people have adopted in trying to deal with challenges associated with sensor networks, ad networks, of course, log shipping, centralization, clickstream analysis. So the sort of thing where data comes flowing in and needs to be captured and maintained and persist at a very high scale. And so all of these become a potential source from which you could issue events and make meaningful real-time actions triggered. In the case of, say, IoT, telemetry, where we talk about trickles becoming a stream, this is where the analogy of a stream is actually particularly appropriate. But what happens in an IoT case is you have a very widely distributed set of small things, mobile devices, sensors, and so on, very widely distributed, and they trickle in drops at a time, small items of data that trickle in individually. But as that scales, of course, those trickles combine and aggregate into a very large amount of data, and this is what we call the stream. And so capturing those trickles and building that stream is a very important part of being able to understand and act upon that data. And of course, persistence is essential. Now, there's generally three patterns against the stream that work and that people are building, and that is archiving, analysis, real-time analytics, small sets of data, providing micro analytics, and of course correlation, quick, simple correlations between data, notifications, and so on. When we think about real-time event processing, the basis of it is, with the stream as an import, that we're driving an event-driven programming model. where events determine next steps and actions. It's very action-centric rather than data-centric. So the activities, essentially we're triggering activities based on those events and the real-time input of the data stream itself. So good examples here are, we described some examples where streaming is already occurring. These are examples where those streams are actually being acted upon in real time. So identifying hardware errors in device logs. So as a change, for example, gets pushed to a wide range of devices, if those logs start to record errors, we can capture those and see that we have a problem in advance of a lot of customers providing that feedback. So this is a great way to get way ahead of a problem that may or may not have been pushed out. And of course, that could then be reversed or rectified a lot earlier with that information. So similar activities in terms of fraud identification, monitoring of performance, shipping SLAs, for example. Is the package tracking at the right place at the right time and so on. Monitor that against the SLA. The benefits are really two main benefits here. One is, of course, whether it's an existing stream or a new one, that you're adding that layer of real-time eventing, taking the data and then acting on it before the analytics layer. So once it's been collected, we do something real with it. Alerts and notifications are very popular. Can be a very simple action, identifying performance and security challenges as well. And of course, automatic data enrichment. Simple aggregations are very popular because the data can be quickly gathered, aggregated, and then moved further down the pipeline. There's another benefit though, because the first one's fairly obvious. The other benefit is the decoupling aspect, the simplification, if you like, of the application itself. By decoupling application modules, breaking effectively functions, triggers and functions, and even larger scale like sets of functions away from the core application, what we're building is an end-tiered application where the functions are very tightly integrated but loosely coupled. So very, very good programming model, very powerful and very maintainable because each function is discrete and can be obviously improved, enhanced, or bugged, debugged, and everything on its own. So the concept of the minimal viable product and iterate, the lean startup, and those sort of adoptions of that approach, very much enabled with this concept. We look at the back end now of the big data pipeline, and we see the data-centric activities really built around the processing of data and the analysis of that data. And there's three core services from AWS in the platform that empower this. And there's a lot of partner-related activity around this as well. And I'll highlight some of our ecosystem so you can observe that. The main services here are EMR, which is Elastic MapReduce, which is a managed Hadoop stack on the AWS cloud. Redshift, which is a petabyte scale data warehouse, very fast, and designed for billion-row queries, essentially, really large queries that against a lot of data. Machine learning is a very new service we just announced a couple of months ago. Machine learning is really a simplified approach to a very complex subject, where the data itself, the developers themselves can take simple inflow of data and teach and train a model into machine learning, and then have good quality predictions come out of that. So very powerful for prediction engines. A few examples of customers adopting these. In the case of NASDAQ, legacy data warehouse, it was extremely expensive. Cost is a main driver for a lot of these, as you'd expect. In this case, they had a limited capacity because it was so expensive. So they only maintained a year of data online. Now, anyone who knows anything about analytics understands that the smaller the data set you've got, the poorer the quality of the analytics, often because you're looking for patterns and trends across a lot of data points. So you may be looking at a billion data points and then essentially aggregating them to 4 or 5 or a few dozen. And so the more data you have, the better. The higher granularity data and the longer that data lasts is a good thing. And so this is obviously a challenge that NASDAQ faced specifically. They implemented both Redshift and EMR, Elastic MapReduce, for different things but related purposes. With S3 as the authoritative data store, Redshift was used obviously to contain and to replace that warehouse. Over 5.5 billion records are loaded every day. On the security side, MapReduce was able to take the address the requirements for client-side encryption and overcome limits with HDFS, which was also a part of that, which is very expensive. So what you can see here is a nice flow of data, both structured and unstructured data, in a way that a lot of companies are adopting. Different paths. The data takes different paths based on its format and obviously the use cases, the access patterns against that data. But what we're seeing is a lot of people having platforms that will service both structured and unstructured, and they integrate. Sometimes they're completely separate. It all depends on the use case. And NASDAQ's a good example of that. Euclid is another example of that, where we can see, again, at the back end, you can see the actual integration arrows there between S3, Redshift, and MapReduce. This is where we see a lot of, say, the unstructured data coming in and MapReduce just being used just to structure that data and put it into Redshift. Of course, MapReduce provides very detailed analysis and discovery for the data scientists, but it can also be used in the form of like a cloud ETL engine to simply structure data and persist that in Redshift, where the data access layer is served by the BI users. So that's a very popular, these three services are very popular in driving a lot of analytics in our customer base. And you can see here by streamlining and making these more efficient, Euclid was able to realize up to a 90% reduction in costs. When we think about the use cases, so we kind of described those primitive patterns, and use cases are really those that span the whole range. They don't necessarily have to go through every stage. Often it's just to collect the data and then start the analysis of that data. But we do have a lot of use cases that become richer over time as they kind of serve their core requirement to start to provide analytics and then enrich it further with higher quality processing, integration, correlation of data in the processing layer, but also more recently to do things like event processing against that data in real time. So here's an example from actually one of our internal staff here is a beekeeper, and he's written a very simple starter app that we share with our customers to help them understand how to build a very basic IoT infrastructure on AWS using the basic services. So here you can see the technical or the physical setup he's got here, Raspberry Pi server, obviously lunch blocks for waterproof housing, and a sensor, a temperature board. And what he's doing there, in conjunction with a little dropcam, which is in the bottom left corner inside the birdhouse. So that's the view you can see from that. So you can monitor this anytime, which is nice from a visual perspective. From a data perspective, it looks like this, or from an architectural perspective. The data is flowing into Kinesis, and then a Kinesis application is consuming that and then persisting that in DynamoDB, which is then driving the dashboard. So that's one part of that data. The other part is really is about notification. And if you understand what's being collected here, temperature information, Lambda is used as a trigger source to identify when anomalies occur and then push a notification through the simple notification service. So that's a great way, great example of a real-time event path as well as a data path from which meaningful analytics can be extracted. So on the Dynamo side, we see a very simple schema. Inside temp, outside temp are kind of the core attributes there, all indexed by a hive number and a date range, which is very normal pattern we see when we're doing IoT or any sort of logging pattern. You see basically a key there, a hash key, a unique identifier, and then a timestamp which delimits that into a range key. How that looks in the dashboard, that's the data view. This is the actual view. You can read a little bit about honeybees and how they warm the hive themselves. The interesting thing here is, of course, where you can see the discrepancy between outside temperature and the very flat linear maintenance of temperature inside the hive. So they're obviously doing their job very well. If we move to another use case, Kaiten Sushiro is if you're familiar with those the sushi trains we call. I lived in Asia for a while, and the sushi train was basically fast food for everybody, good fun. What these guys have done is taken it a step further and put sensors at the bottom of their plate. So the color of the plate determines the cost of the sushi. That's how it's been for a long time. And what they've done is put sensors on the plate so they can grab that information in real time. So what they're doing is very simple. I talk further about how you don't have to do all the interim steps, and these guys aren't at this point. What they're doing is collecting the data, centralizing the data via Kinesis, and then just persisting that into Redshift so they can run analytics against it, in this case using a Tableau front end. They could, of course, add richer processing. They could add real-time eventing, but this is their core process, their core pipeline, and that's perfect for their use case. And so this is the point about big data. You don't have to start big. You know, the data itself presents enough of a challenge that you know, starting very simple and then iterating and enriching the model is a really good approach. As we talk about more commercial applications of this or larger scale, dropcam is a great IoT customer who experienced a petabyte scale growth in the data that they ingested. Why I really like their example is because their architecture is almost a perfect reference architecture. In the case of real-time streaming of live video, that's all done on, you know, it's compute memory, and EC2 is the basis of that. But if for subscribers who subscribe to their 7 or 30-day subscription package, that data is then stored into what they call CVR, Cloud Video Recorder, where the larger files are maintained in S3 and the indexes are built in DynamoDB. And so that you have a very fast search capability in Dynamo against a large file data store in S3. And that's great. It works very quickly. And when files you're on your phone and you want to see some video, they get delivered through CloudFront. CloudFront is a CDN, a content delivery network that will bring the files closer to people wherever they are around the world. It's essentially caching it at the edge. And what that means is you get a very fast experience replaying a potentially very large file. EMR is a further enrichment, MapReduce enrichment they added on top of this infrastructure, and it's basically to do the high quality analysis against that data stream to say, recognizing simple events. You know, here was movement, let's tag it so it's easy for the consumer to find, you know, things to look at and identify movement and whether you should be concerned or not. But there's other things that they've applied for that. Activity recognition, recognizing frequently occurring activities and being able to essentially block them out. Say, it happens all the time, so don't notify me about that. So this is a great example of getting the core real-time data processing working and then adding higher level of analytics on top of that further enriches the real-time experience. When we move from a kind of more consumer-centric IoT to a commercial approach, there's a lot of legacy gateways and infrastructure in industry. Like if you think of oil and gas, pipeline monitoring, things like that, this has been around for a long time because these are very, very serious production systems. And they've often relied on these gateway services that essentially provide a much lighter footprint for data communication. And so MQTT is a great example of that. And so the cloud provides a perfect opportunity to put that broker inside the cloud, so you still have the accessibility that you had previously. You just don't have to host the infrastructure. And once it's there, of course, you have access to the platform behind it, all those services to enrich and enhance the quality of that data as it flows in. So what it would look like in a back-end analytics architecture for such a use case, really the case here where, again, Kinesis is capturing that unstructured data and having worker nodes persist that in DynamoDB. And the reason you do that is because there's an interaction process that goes on here. And in this case, we're taking a legacy application in the corporate data center that needs to interact with that data. And so DynamoDB, by pushing it into DynamoDB, it's now structured, and the legacy app can interact with a database, structured data, and understand, you know, each attribute individually and make queries and put skets and queries against that data. Now the data also then flows downstream from there, flows out via an analytics process powered by MapReduce, which would then take the data and add enrichment and structure to that data, persisting it into S3 and then loading it into Redshift. Now why you would persist it in S3? Two reasons. One is it's the fastest way to get data into Redshift, but two, you'd want to leave it there for offline archiving and then maybe flow that down into Glacier at a later date. And what we're talking about there is very low cost storage, cold storage, at a very low price. That's what low cost is. So that's a good reference architecture for device data, and we're seeing a lot of adoption of these sort of architectures. And we think about big data. It's not just about the things that we have, the services that Amazon has that help. You know, we align to those collect, store, process, and analyze paths in the big data in the big data pipeline. But surrounded with this are a lot of ecosystem partner options where customers are adopting and then integrating into these applications and services as well. So you can see some of them on the screen there. A lot of them are preferred partners with AWS. So you get the opportunity there to work with partners through AWS because we've established those relationships and then present that into what we call the AWS Marketplace. Now, if you're not familiar with the Marketplace, it's simply a way where all the AWS partners basically publish their data and make it available in pay-as-you-go pricing. So it's very accessible because it's in the marketplace, in the cloud, so it's accessible one click around the world, but it's also on pay-as-you-go terms, pay-as-you-go pricing, so there's no long-term commitment. Now, this is a way where our ISV, or independent software vendor partners, publish their software into our marketplace so the customers can access it if and when and how often they need to. So it's been a great way for customers to build not only the core infrastructure of their big data pipeline, but also append that with really useful business intelligence, data movement, advanced analytics around the pipeline to get a much higher quality result. So when we summarize the big data platform, I think the three main important takeaways are really about the way we architect it, and specifically around choice. Choice is very important because it obviously supports as many variants of use cases as you could imagine. Choice is very important because it allows you to not have to, say, work with one container, one relational database. You can work with a NoSQL database because it's suited for that, and a data warehouse because it's suited for that. So this choice is very important in allowing the second point, which is specialization, the ability for workloads to interact with their data in a way through a platform, through a service that is specialized for their use case. Do a billion-row queries in a traditional relational database is not a good pattern for that database. It's going to be expensive. It's going to not work for a while. It's going to hit a ceiling because they're not designed for that. But a warehouse is. But when you have rich transactions and joins, complex queries against relational data, perfect for that. And we've talked about different use cases with things like dynamokinesis and S3 as well. So this is kind of the value of having a wide choice of highly specialized services. The final point is really that they are managed. So it may be more efficient and certainly a better experience to have more services dealing with specialized parts of the workload, but the management, the administration of those has traditionally been very difficult. So this is why the AWS platform includes these as managed services, where anything from 60 to 90% of the effort associated with the underlying infrastructure is completely eliminated. In some cases, it's 100% for users. It really depends how much is required. And so this gives a very efficient, highly productive platform for users to adopt. It gives them the ability to build specialized services for their customers. And most importantly, it eliminates the bottlenecks that have traditionally prevented high-scale use cases from reaching their potential. So with that, we're going to turn it over for questions. Thanks for attending. We've got some questions in the chat window, and we've got a few minutes to address them. So I'm going to have Eric read out a few of the questions, and we'll address them for you in real time.
Sure. So the first question is, are you able to run HDFS in AWS and the AWS Big Data Platform? And what are other potential alternatives to HDFS?
Yeah, great. And I might ask you to append my answer. Eric's far better in that area than I. But yes, so EMR, Elastic MapReduce, is a managed Hadoop. So it's the whole Apache stack. We also have distributions for MapR and others. So yes, HDFS is definitely part of that. HBase is part of that. But what are your options? You can always persist the data into S3. EMR talks directly with S3. And I think there's another file system there we've got, Eric.
Yeah, correct. So by using S3, essentially, so basically the two options are to basically run HDFS locally on the EC2 ephemeral drive. So it looks very similar to a physical environment where you run HDFS locally with three-way replication, etc. And then the secondary option, and kind of as Dave indicated, is to basically use S3 as your HDFS. So we've essentially used the open connectors and open APIs to make the cluster think that S3 is the HDFS. So this gives you all the benefits that come along with S3, namely very low cost. Secondly, the ability to both add and also remove nodes on the fly because the data is no longer stored locally. And then thirdly, also the ability to just leverage the automatic replication and high durability of S3. So those are kind of the advantages and reasons that you can do those two options.
Yeah, thank you. And we do see a lot of that. So it depends on how much of the Apache stack, the Hadoop stack you want to manage. But it's all there inside EMR for you.
So another question for you, Dave, is Kinesis similar to an ETL tool?
It could be, but I think it depends what you do with ETL. ETL stands for extract, transform, load, which is typically the interconnect between business applications and the data warehouse. So in that regard, I would probably say no in the classic regard, but also ETL tools have evolved substantially since those times. So for the newer applications of ETL, yes, they're much more overlapping into the Kinesis space. Kinesis is perfect for that first point of ingestion. Data is maintained in Kinesis for 24 hours. It operates at any level of scalability required. And usually the point of the ingestion part of a big data use case where data is created outside of the infrastructure, just collecting that data represents the primary challenge. So yes, depending on how you deploy your ETL tool, yes, in a very, very traditional sense, relational database into a data warehouse, not so much.
Next question is, does Redshift store data locally or in S3?
Great question. Both is the answer. So Redshift is a cluster, and it sits on top of EC2 instances, but all the data is local to the instance, by which we mean it's maintained in the cluster, and that's really because we need it to run very, very fast. But in addition, so one point about Redshift, inside the cluster we maintain 2 copies synchronously of the data because we're talking about a lot of data, a lot of disks, whether they're magnetic or SSD. Hardware fails. So when we do have failures of the hardware, we have basically seamless and transparent failover to the secondary, which is maintained within that cluster while we repair, again, another secondary for operations. But the data is also constantly flowing into S3 as a backend. And so you can do that, you can use that in a number of ways. It's very easy, for example, to stand up a cluster for, you just want to test some stuff, but you don't want to hit the production data warehouse. You could just hydrate a new cluster from that snapshot. It could be in a different availability zone, it could be in a different region. So yeah, there's a number of advantages to that, but essentially, yes, the answer is both, and for the reasons I outlined.
Next question is DynamoDB more like a document store, or is it more relational?
DynamoDB is more like a document store, but it's also, so relational databases, the big difference between NoSQL, which is a bad term, because SQL is just an interface, right? NoSQL should be called non-relational. Now, the thing about non-relational databases is that they don't have those cross-table, the awareness of multiple tables, so foreign keys and so on. So you can't join across tables. There's no reason we couldn't build that into the interface, but you're losing kind of the value there. When you take a relational database and you scale it, one of the steps you do is denormalization, which is essentially eliminating joins. You're making data maybe more redundant, but you're putting it in one table. And that's a key tenet to high-scale database interactions, is that denormalized data model, single table fetches. So DynamoDB supports 3 types of data interaction, or really data storage. One is the key value, where we have just a key and a payload, very, very high scale. We call that key the hash key. Which is also the primary key. We also have a primary key model that's composite, where we have a hash key plus a range key. And I showed you that in the B example there, where the hash key is what we use for distribution, but the range key is like the child and the parent-child relation. And against that range key, we offer rich query capability, begins with greater than, less than, and so on. So that's where we support the kind of one-to-many relations within a table itself. But we've also added full document capability there, in that you can define a JSON document and store that natively in DynamoDB, and the full map of that document will be expressed and readable and accessible in DynamoDB. And so essentially what that gives you is the nested one-to-many relations of JSON. So it's a document store, it's a key value store, it also has simple relations as well, but it's definitely not relational. Okay, no, I think we're close to time, so appreciate everyone's attendance. Sorry for the technical problems at the outset, but provide your feedback. I think we've got okay, yep, we've run the survey, so please give us your feedback and stay tuned for something else. Look out for more webinars to come. Thank you very much. Bye bye.